Okay, thank you, Marcel, for the introduction. First, I would like to show very briefly the structure of our company and where we are placed inside the group. Here you can see the 5 divisions, and we are part of the division Sensors and Actuators. Now you can see the agenda. I would like to say a few words about the project, and then will I go directly into the modeling of the DuoCam. Furthermore, my colleague Artur Hottmann will present some well-trained features. After that, he shows the whole simulation model and some results. He will conclude with a summary and the next steps. The DuoCam is an assembled camshaft that enables the timing of one set of cam loop to be moved relative to a second set of loop. That means that the DuoCam is used to change the valve timing. This has certain advantages on the engine performance. NOx emissions can be saved through targeted timing of the valve. Thermal management strategies can be implemented to reduce CO2 emissions. The Miller process is realizable. And finally, all these measures has a positive effect on the fuel consumption. Here you can see the CAD model of the DuoCam and a sectional view. The DuoCam consists of a concentrically arranged outer tube and an inner drive shaft that can be phased. There's a radial clearance between the inner drive shaft and the outer tube. If we look a little bit more detailed into the different parts, you can see the outer tube with the journals and the fixed lobes. A so-called moving cam is arranged in the middle of the figure. The moving cam is connected with the inner drive shaft via a pin. The pin is guided through the outer tube via a slotted hole. The oil film has to be considered between the components of the moving cam and the outer tube. On the next slides, I would like to show the goal of the project and how we build up the model of the DuoCam in GT Suite. The aim of this project is to build an assembly of the DuoCam as a 3D multi-body simulation model in GT Suite. With increasing complexity, it is necessary that the model must work very robustly. The model is used for multi-body dynamic analysis with elastic components, and we want to investigate the drag torque behavior for the DuoCam. Furthermore, it is possible, of course, to combine the model with a virtual engine to consider the elasticities of the whole valve train to the load change. The challenge in this project was to implement the structural mechanical properties of the DuoCam correctly. Moreover, it is necessary to integrate a cylinder deactivation mechanism because we want to use the model of the DuoCam at different firing sequences. Here you can see the GT Suite model of the DuoCam. At this position, we do not yet consider the valve train. At the top of the figure, you can see the inner drive shaft, which is divided in several segments. Connected to this are the pins, which are connected to the respective moving cam. The moving cam, in turn, is connected to the outer tube. The outer tube includes the different journals and the fixed lobes. Now I want to show you some modeling details of the components. First, we look to the modeling between the inner drive shaft and the moving cam. The shaft segment of the inner drive shaft is connected with a 1D, 3D connection and a dummy inertia to a massless torsional spring. The torsional spring transfers the power from the inner drive shaft to the moving cam with a very high torsional stiffness. The 1D and 3D connection and the dummy inertia were also used to connect the torsional spring with the moving cam. The inertia elements will also be necessary to connect for the connection between the different templates. On this slide, you can see the connection from the moving cam to the outer tube. Between the components is a radial clearance, and in this radial clearance, it is necessary to model an oil film. At this point, we had a problem because it was not possible in version 2021 to connect the inner diameter of the cam lobe with the outer diameter of the journal bearing. GT has supported us and developed a patch that makes this connection possible. From V 2022 onwards, this is an available standard connection in GT Suite. Now the journal bearing is used to transfer the friction forces over the old film and consider damping effects. After that, it is necessary to connect the journal bearing with the journal element. The next challenge was the integration of the structural mechanical properties into the GT Suite model. Of course, GT Suite calculates the structural mechanical properties for the parts of the camshaft, but only for a common geometry. Due to the arrangement of the concentrically shafts of the geometry of the DuoCam, this geometry deviates from a standard camshaft. At the position of the pin, which is connected with the inner drive shaft and the moving cam, there's a hole in the inner drive shaft and a slotted hole in the outer tube. And this results in a lower stiffness for the camshaft. Therefore, an ANSYS software tool was used to calculate the torsional and bending stiffness of the DuoCam more accurately. If you look now to the template, you can see an input for the torsional stiffness, but not directly an input for the bending stiffness. At this point, we have to find a workaround to convert the bending stiffness from the ANSYS tool and enter them as beam properties into GT Suite. The GT Suite Excel sheet beam prop data helped us for this conversion. Sorry. Now we must ensure that the transferred structural mechanical inputs from ANSYS are plausible. Since no measurements were available at the time, it was necessary to compare the results with a standard calculation by the GT Suite solver. To simplify matters, we only integrate cylinder 8 at the end of the camshaft. On the right-hand side, you can see the lift loss of the intake and the exhaust valve for cylinder 8. A negative value means a lift loss of the DuoCam with the data calculated by the ANSYS tool compared to the standard calculation of the GT Suite solver. The lift loss is very low and plausible with a maximum of 5.5 microns at 5,800 APM. Next, I would like to hand over to my colleague Artur.
Thanks, Frank, and good morning, everybody. On this slide, I want to show you, or on the next chapter, I want to show you how we integrated the firing fraction sequences. And yeah, the mechanism is implemented or allows us to deactivate the movement of the valve on a fly, like shown here on the right side. So the main part of the mechanism is the HLA, and this is located in between the roller and the plunger at the top. In between, you can find the latch pins. The latch pins are for the base circle in clearance to the lifter housing, and at the top you can find a stopping surface. This one absorbs the forces, so the HLA is not charged additionally. So what does happen if the cam lift is locked? The latch pins are loaded and transmit the forces to the top, and since the valve journal at the top is fixed, the valve's open. So now it's getting interesting. If we want to deactivate the mechanism, we put the latch pins inside, and the HLA and the spring will balances the forces. So the latch pin, the valve will not open at this point. So let's have a more detailed view. On the left side, you can see an activated mechanism. On the right side, a deactivated mechanism. On the really right side, you can see how we implemented this in GT. At the top, you can find the HLA, at the bottom, the roller. So there is a lifter component, which is connected to the top of the HLA and the bottom of the HLA. At the top, you can also find the stopping surface. So what's in between here? We integrated a inertia box with a special design and also the latch pins. The latch pins can be pushed outwards and inwards. This is the difference between the deactivated and the activated mechanism. If we push the latch pins inside the spring, under the latch pins will be compressed. And there are also several components integrated for the controlling. We have a detailed view on this later. First, I want to show you some results. You can find here the volume of the HLA compared to the valve lift at the top. And here you can get an insight of the refilling of the HLA. In the first cycle, you can see a very high oscillation. This is because of the initialization of GT. And over several cycles, you can see the volume stays very constant. This ensures that the mechanism works very robustly at this point. How did we integrate the controlling? We have used super parameter. Super parameter can contain several definitions like the cycle and also the firing fraction table here at the bottom. We implemented this like from an Excel sheet just by simply copy and paste, and so the user can just modify the controlling of the firing fraction from outside. Everything is controlled by an algorithm, and I want to explain you this on this slide. So the shifting process of the latch pins is not implemented mechanically, so it's calculated by the algorithm, and so accordingly the forces on the latch pins are calculated by GT. This can cause really, really high oscillation, so we need a very robust solution at this point. And since the shifting process can only be done on the base circle, we implemented the following solution here. So the shifting process just starts opposite the peak position, so 100 degrees later, and ends just before the profile rises again. The firing fraction table indicates here in the lookup table, and everything is controlled by a math equation. And also there is a RLT sensor integrated for a better overview and the full model. So in the next chapter, I would like to present you the full model and also some results. So now you can see the full valve train, including 8 cylinders. And also you can find here the deactivation and activation mode. So let's shift this to the side and see the full model. Now you can see also the valve trains are integrated in the full model, and note the just mentioned deactivation mechanism is here implemented as submodel. So how does this affect the valve lift? Let's have a closer look to the valve displacement. On the left side, you can find the first 4 cylinders. On the right side, the last 4 cylinders. And the exhaust valves are colored red, and intake valves are colored blue. So this is a specific firing fraction, 3/4 at 3000 RPM, and this controls that 1/4 of all cycles are deactivated over the time. So which cycle is deactivated changes every 4 cycles, like shown here in the different colors. So how does this affect the drag torque? We have here a comparison between the standard cam, which is validated by the test rig, and also our DuoCam. And since there are holes integrated in the DuoCam, we have a slightly lower stiffness for bending and torsional. And so if we have a closer look to the amplitudes here, we can see it's slightly lower compared to the standard cam, and this is absolute plausible at this point. And also we have a really good agreement in the characteristics. So finally, I would like to present you chapter 5, the summary and the next step. We successfully built up the model in GT. We got great support by G as well, and we integrated further features like the torsional and bending stiffness from the ANSYS analyzers, and We also integrated a very robust solution for the deactivation mechanism, which is modifiable by the user from the outside, very modular. And also the simulation model provides the right drag torque for a signature to the camshaft for the different firing orders. And the next step, of course, is to check this characteristics with data from the test rig. Finally, I would like to thank some colleagues from GT and from Rheinmetall. Thank you for your attention, and yeah, don't hesitate if you have any further questions. Thank you.
Yeah, thank you very much for this very interesting presentation. Yeah, I think we have time for 1 or 2 quick questions, if there are any in the audience.
Michael Pranzel, Porsche Engineering. Thank you for the presentation. I like a lot what you have done on the World Train side. I have one question regarding the purpose of the simulation. Was the main target to simulate and investigate the drag torque, or was the target more to investigate the hydraulic adjuster itself, maybe the loads on the pins, etc.?
Yeah, well, the drag torque is the way we can just identify if the model is working correctly, since we don't have really data, measured data for the DuoCam, so we can compare it to the standard cam, which was already measured. So this was the way to do. Yeah.
Perhaps I can extend. I have an additional note. Of course, the main target was finally that we combine the DuoCam model with a valve train together with a virtual engine. And we do this for the customer, and finally the customer will use this valve train model. But this is a future task because we have first, it is necessary to compare it with measurement values.